alaikum. Good afternoon. My name is Christophe. I run the business development for Pascal around the world. So let me just introduce Pascal. Pascal is a French scale-up founded in 2019 by 5 co-founders with the Nobel Prize of Physics, Alain Aspect. So we are really proud of that, but this is not the topic of today. I'm going to talk about quantum, not in terms of physics, but in terms of security, regulation, and what is typically a risk or an opportunity. So the convergence of quantum technology and encryption present a critical security challenge. I will highlight an important concern about quantum computing, potential to undermine our current cryptography system. This threat is particularly significant because many of today's encryption methods like RSA or ECC relies on mathematical problems that classical computers find difficult, but quantum computers could potentially solve efficiently. This vulnerability is often called harvest now, decrypt later, where enemies collect encrypted data today with plan to decrypt it once quantum computers become powerful enough. The security implications are far-reaching for financial institutions, protecting transaction data, healthcare organizations, safeguarding patient information, government agencies, maintaining classified communications, corporations protecting intellectual property. Effective governance approaches might include: 1, mandating post-quantum cryptography migration timeline for critical infrastructure. Second, creating quantum-resistant standards through organizations like NIST. Third, establishing disclosure requirements for quantum computing breakthroughs. And finally, developing international agreements on quantum technology usage. Regulatory frameworks will need to balance innovation with security concerns. Quantum technology offers tremendous benefits in fields like drug discovery and material science, so overly restrictive regulation could hinder beneficial progress. Before to move on, I would need to detail what are the 3 main topics in quantum. Here, I will not talk about quantum sensing. I will not talk about quantum communication. I will only talk about quantum computing. The quantum computing threat to our current encryption infrastructure requires multiform answer. Let me elaborate on the key dimension of this challenge. First, before exploring much more this quantum computing field, let me give you a brief definition of the segmentation with this quantum market. First, hardware, so specialized equipment use quantum computing similar to on-prem cells like NVIDIA do with GPUs. Cloud access to quantum computer capacity in order to serve use cases, and then services around consulting, proof of concept, and ad hoc software and algorithm development. So how to position quantum computing in that field? First, we need to talk about the technical vulnerability. Modern cryptography largely depends on algorithms whose security is based on mathematical problems that are computationally difficult for classical computers. RSA relies on the difficulty of factoring large prime numbers. ECC, for elliptic curve cryptography, depends on the discrete logarithmic problem. And many digital signatures use similar mathematical foundations. So quantum computer, particularly those leveraging Shor algorithm, could break this cryptography system. A significantly powerful quantum computer could factor large number exponentially faster than classical one, rendering this protection outdated. So what could be the timeline and the urgency regarding this? While fully capable cryptographically relevant quantum computers don't exist today. Progress is accelerating, by the way. IBM, Pascal, and others have demonstrated quantum computers with increases qubit counts. Error correction techniques are improving as well. Estimates suggest that within 5 and 15 years, so 1-5, quantum computer may be able to break current encryption, not before. The long-term nature of some sensitive data, health record, defense information, financial transactions, means organizations must act now and not tomorrow. As information encrypted today may remain valuable when quantum decryption becomes sustainable. Then we need to talk about the implementation challenges. The transition to quantum-resistant encryption tackles significant barriers. One, legacy systems that cannot be easily updated. Second, supply chain dependency, where vendors control encryption implementations. Third, resource constraints, especially for smaller organizations. Validation and testing requirements for new cryptography implementation. And finally, balancing security performance as post-quantum algorithms require more compute resources. So organizations definitively will need comprehensive quantum risk management program that prioritize systems based on data sensitivity, expected lifetime, and upgrade complexity. The progression of quantum computing technology follows a path that directly impacts encryption security, with each advancement bringing us closer to breaking current cryptography system. So let me first define what FTQC means. FTQC means fault-tolerant quantum computing that represents the ultimate goal in quantum computing development. Then, we need to work on error correction. FTQC system can detect and correct quantum error through redundant encoding of quantum information. Then, to do that, to do the computation, we need logical qubits. Multiple physical qubits work together like atoms in Pascal technology of qubits to create more stable logical qubits. And then the scalability of system can maintain quantum coherence across large number of qubits. So the transition from today, noisy intermediate scale quantum, named NISQ, devices to FTQC involves overcoming significant engineering challenges in qubit quality, error rates, and control system. How quantum computing will break encryption at the end? Certainly, there are two sorts of algorithms. The first one is Shor algorithm. Shor algorithm provides exponential speedup for integer factorization. A quantum computer with several thousand logical qubits could break an RSA encryption, already demonstrated in lab at small scale, but not at a large scale. Via a Groover algorithm, certainly. A Groover algorithm provides quadratic speedup for brute force attack on symmetric encryption. But maybe the most important, the timeline. Major research institutions projecting 5 to 15 years until cryptographically relevant system could really work. Let's step back. Is it a real risk or an opportunity? In reality, quantum is a major opportunity to a business value standpoint. It represents around $800 billion of potential value over the decade. Here in front of you is the decomposition by large segments. First one, simulation. The idea then is how to use a quantum computer to simulate the nature, the physics, the chemistry. Second pillar, optimization. How to resolve complex problems like logistics, scheduling, grid management for telco and energy organizations. Third, machine learning. How to integrate quantum algorithm into a classical AI workflow. And finally, cryptography, which, as you can see, which represents only the last segment of the total value market. Interesting, isn't it? I think it's also a major opportunity to learn quantum computing until FTQC time and a possible risk associated. As an example, many verticals could be nominated. At Pascal, for instance, we already explore more than 40 use cases, and you have in front of you different examples where we got some tangible results with real machines. Also, quantum computing could be seen as common pillar of AI, where AI quantum enables AI. Secondly, how quantum computing could help HPC, so mega computer, to be more efficient by finding some hybrid methods. And finally, by providing a new proposition due to low electricity consumption, like Pascal technology, for instance, as a game changer in the green transition field. Quantum computing is ready to transform global industries: energy, logistics, material science, finance, and many others. Now it's time to get some advertising as a joke. So I will end my talk by showing through this picture a real Pascal computer. So this is a reality of today. It works, and we have already deployed machines around the world. For your information, you could have access through the cloud to this kind of machine. As an example, we are going to install the most powerful machine by the end of this year in the Middle East region. This type of machine works at room temperature, so you could install it in your kitchen if you wish. Just need 4 plugs, equivalent to 4 air dryers, so an equivalent of 10K watt. And finally, if you would like to learn more about our quantum technology, about quantum computing, and be ready to tackle the crypto risk, if any, please flash the QR and see you around our Pascal community platform. Thank you.